Welcome to Engineering Graphics Pictorial Lecture. My name is Jasmine Lay, and I will be your instructor for this lesson. The objective for the lecture will be to identify axonometric and oblique projections, learn how to represent a three-dimensional object effectively on a two-dimensional drawing surface using pictorials, learn how to visualize a three-dimensional object using solid primitives. In general, we will be reviewing perspective versus parallel visualization. We will detail axonometric as well as oblique projections. We will talk about how we use them and how to create them, and where they can be found in our 3D modeling software. Recall our roadmap to visualization. All projections can be divided into two theories of thought: perspective and central projections, or parallel projection theory. The first visualization lesson covered perspective projections as well as aerial perspectives. Secondly, you learn about orthographic projections, specifically multi-view drawings, which are most beneficial to all engineers. Today, we will cover both axonometric projections and oblique projections, which are different types of parallel perspectives. Let's begin by understanding or recalling the four principal projection techniques. Perspective projection, as stated before, has an observer's eye as a means of conversion for all lines of sight. Everything seen in the picture plane on the object appears realistic. For the most part, this type of visualization method is used in art and advertising. It gives the customer a realistic perspective of the 3D model. The second type of projection technique is the orthographic or parallel projection, titled Multiview Projection. As the observer is placed at infinity, parallel lines of sight are drawn to create various views. The camera method comes to mind, from which an engineer can describe both the top, front, and right side view of the principal planes of the 3D object. This type of projection method provides details in tolerancing and dimensioning and has been standardized by various agencies such as ASME or ISO. The third type of principal projection is the orthographic projection technique, titled Axonometric Projection. It is similar to a multi-view perspective in that we have a parallel line of sight. However, we have a rotation of the object that provides a three-dimensional perspective rather than one view of the object. Axonometric projection provides an axis as a relation to a picture frame. In this image, one can see the picture frame can provide a multi-view drawing from a projected image from the 3D model, and if the object is rotated, an axonometric pictorial can be gathered. Axonometric classifications are founded on what are called axonometric axes. The first trimetric pictorial has no equal angles, no equal corners, but is the most visually pleasing and the most difficult to produce by hand. The dimetric pictorial generally has angles A and C as equal angles, as can be seen from the image. Lastly, the one we will be learning to create in this class is the isometric pictorial. Isometric pictorials generally break up the axis into equal 120-degree angles, after which a depth is drawn to provide details of the three-dimensional object in a two-dimensional plane. These angles can be seen in SolidWorks. Notice how in SolidWorks you can switch orientations by hitting the spacebar. The dialog window pops up and shows you isometric, trimetric, and dimetric views. That's an isometric view of this rail button. This is a trimetric view of the rail button. And this is a dimetric view of this rail button. If I have a cylinder, I can see a trimetric, dimetric, and isometric view. When drawing by hand, one can begin an isometric pictorial sketch by utilizing an isometric scale ruler. These are generally available for draftsmen and civil engineers. For the most part, the plan is always to begin generating your axis with a separation of the 120-degree angles. The easiest way to do this is by creating a 30-degree face from a horizontal plane. Additionally, step 2 involves adding width, depth, as well as height to define step 3, a bounding box. Once your bounding box is created, features of your object should appear. Details can then be displayed and the removal of your bounding box, which generally involves an eraser, complete your object. As easy as this sounds, the process is generally complicated by curved features. Circles are generally reflected as ellipses. Beginning with a bounding box, major and minor axes are drawn to provide guidance for circles. Notice how the images representing correct and incorrect methods of drawing circles are shown in this slide. Isometric cylinders are drawn in a very similar manner. Starting your bounding box, adding your sketch of the front face of the cylinder, then the rear end of the cylinder, followed by tangent lines. Once the object is created, the bounding box can be removed to finalize the sketch. Isometric ellipses, like the ramp shown here, follow the same procedure. Additionally, you can purchase what is called isometric paper to create sketches. Take the time to print this one out and attempt an isometric pictorial problem from the links provided in Blackboard. The last of the 4 principal projection techniques is the oblique projections. This involves parallel lines of sight for the picture plane, but what differentiates this type of projection from an axonometric is the fact that the front face of the projection is always true to size. In other words, when looking at the chair, one can create an orthographic drawing, meaning a multi-view drawing showing the front face of the chair. What an oblique perspective does is add depth to that view. This depth can be seen in this perspective image. Notice how the chair has not been rotated or changed in comparison to the projection plane. The only detail added has been the depth to that front view. The depth is generally added at a 45-degree angle, which is why when drawing oblique projections, you only need quad or engineering paper. Oblique projections are the simplest to draw. Although the natural view of the object is shown, the projectors, which can be drawn at 30, 45, and 60-degree lines, generally add some distortion to the image. As stated before, the 45-degree projectors is the most common and will be used in your assignment. Oblique drawings can be classified based on depth of these projectors. There are 3 classifications based on depth: cavalier, which is a full size of the object; cabinet, which is half the size of the object; and general, which can be drawn from full to half size of the receding axes. Here's an example of a cavalier, cabinet, and general oblique. Notice 3 things. 1. The front face of the object is true to its shape, so the circles are circular and not elliptical. 2. The depth of all 3 objects is varied. And 3. All of their depths are drawn at a 45-degree angle. Here's an additional example of a cavalier oblique and a cabinet oblique. Once again, notice the front face, depth, and angle of this depth. For your benefit, take the time to download the exercise seen here of an oblique pictorial. Attempt it at home, as you will have similar homework assignments as well as midterm and final questions involving oblique pictorials. This ends our lectures on visualization theory. Recall all 4 of the projection methods. Understand how they relate to the line of sights, as well as whether they have a principal plan of projection. Their application is important for you as an engineer. You would not be using a multi-view drawing as a single view pictorial for marketing purposes. Most of the general public would not understand. Take the time to review the rest of the information for your quiz and midterm examination.